Hello, and welcome to my presentation. My name is Arthur Carvalho, and today I will be presenting the paper Selecting the Optimal Number of Crowd Workers for Forecasting Tasks. This is a joint work with Dr. Majid Karimi from California State University, San Marcos. Our work is about crowdsourcing, or how to outsource a task to a crowd. Of course, a crucial component in crowdsourcing is the crowdsourcing platforms, because they give employers access to a global population of workers at virtually any time. So we have platforms such as Clickworker and the very popular Amazon Mechanical Turk. Some of these popular crowdsourced tasks are data labeling, data collection, such as in behavioral experiments, sentiment analysis, among some others. There are some crucial factors related to crowd composition that will determine if a crowdsourcing project is successful or not. For example, the diversity of the crowd, if the crowd has enough people who have different cognitive processes. We also have the skills of the crowd workers and the size of the crowd. Our work is related to the last factor, the size of the crowd. And specifically, our guiding research question is, how can one determine the optimal crowd size? And the tasks that we are interested in are primarily forecasting tasks, where the crowd workers, each one of them individually, they report a single number. This number can be a prediction of the attendance for a specific event, or an asset price in the future, and so on and so forth. The specific task doesn't matter for us as long as it is a forecasting task where the crowd workers report a single number. There are some challenges in that specific setting. Number one, the first challenge is that traditional statistical techniques that work ex ante, such as power analysis, are not necessarily appropriate to determine the optimal number of crowd forecasters one should hire. And the second challenge is even the idea of optimality, to define what optimal means, because optimal can have different meanings. So we address these two challenges in two different ways. First, number one, our first contribution in the paper is to formally describe how the number of crowd forecasters relates to the expected forecast error. That produces what we call the error curve. And using this error curve now, we can determine the optimal number of forecasters one decision maker should hire. However, we still have to define what optimal means, and that is the second contribution in our paper. We provide a novel optimality concept that relates the number of crowd forecasters to the desired or tolerable variable error by the decision maker hiring the crowd forecasters. And throughout the paper, we also have one illustrative study related to sports forecasting. Now, with that being said, let me introduce our mathematical model now in an oversimplified way. So we have a group of n, a number n of crowd forecasters, and as I said before, each forecaster I, indexed by I, reports a single number, a single point estimate that we call in our paper Fi, and that's just a real value. The idea here is, and perhaps the number one and most important question, is that if we have a random number of forecasters, like G, we randomly select G forecasters from the crowd, we take their predictions, their forecasts, their numbers, and we aggregate them, we average them. The question now is, how good is that average? So what we can show in the paper is that that average is determined by two errors. We call epsilon G the expected error produced by a group of G forecaster, and that expected error can be decomposed into two errors. The first error we call alpha. That is a fixed irreducible error. So there's no way for us to play with that error. The second error that we call the reducible error is a value beta divided by G. So we can play with that specific error. We can increase the number of crowd forecasters, and as we increase that number, that error will go down. So just to illustrate proposition number one, we have one illustrative study in the paper where we hired a total of 50 workers from the crowdsourcing platform Amazon Mechanical Turk, and we asked them to make a prediction on the outcome of an NBA game. We asked them to report the probability, a number between 0 and 1, that the home team would win the game. After the game was over, we were then able to estimate the error curve. And the error curve looks like what I have in my screen now. We can see how the error curve goes down massively when the number of crowd forecasters increase, but eventually it levels off. It becomes almost flat when we increase that group size right there. And the error also will not go to zero. Eventually the error converges to this kind of a red line that I have in my screen, and that is the irreducible error that I have in my screen now. At this point, we still have the question, how many crowd workers should we hire? Should we perhaps hire the maximum number there, which in this case would be 50? And what we argue in the paper is that hiring the maximum number of forecasters make not much sense in practice. Because in practice, in real life, we have budget constraints. We cannot really hire everybody because maybe there is not enough money available. And the second point and second crucial observation in our work is that the marginal gains in variable error reduction, they decrease massively after a number of crowd workers are hired. Just to illustrate this second bullet point a little bit better, we have this plot in our paper. What this plot shows is the reduction in the variable error after hiring a number of crowd workers. For example, if we hire 2 crowd workers, we have these data points right here, this dot. If we hire 2 crowd workers, we have a reduction of 50% in the variable error. Now, if we hire 5 of them, that number goes all the way to 80%. However, if we hire 30 of them, 30 on, you can see that there are only marginal gains in hiring 1 extra crowd worker. So we leverage that insight to develop equations and formula that will allow us to select the optimal number of crowd workers. But first, we still have to define what optimality means. So in our paper, the formal definition of optimality is as follows. We say that a certain number is gamma optimal, like a number y, if we say that the number y is gamma optimal when aggregating the forecasts from y crowd workers leads to a reduction of at least gamma of the total variable error. So the mathematical definition can be a little bit hard to parse, so let me give you one example. Say that we have a requester. The requester is willing to accept at most 25% of the total variable error. In this case, the requester, the person who is hiring the crowd workers, wants the total reduction in variable error to be at least 75%. So if we go back to that previous plot I have in my screen, this crucial plot right here, it means that the decision maker or the requester hiring the crowd workers, that person wants the total error reduction to be at least 75. Which means we have to hire at least 4 crowd workers to satisfy that desire. So with that being said now, we can formulate our solution mathematically as follows. We have an optimization problem where we try to minimize the total number of crowd workers we hire. That's y is a number, positive number. We try to minimize that number such that this constraint here is satisfied. What this constraint says is, if we take gamma right here, which is the desired or the tolerable variable error by the decision maker, that error is less than Sy. So what is Sy? Sy, we show what it is in the paper. It is the cumulative variable error reduction when higher y crowd workers. So putting this again in words, what we're trying to achieve here is we're trying to hire the smallest positive integer y such that the cumulative error or the variable error when we hire y people, the reduction in that error is greater than the desired error by the decision maker, which we call gamma. Okay? So with that model, we can use that model in practice in 2 different ways. So first, we can have a fixed number of crowd forecasters if we have, let's say, 5. Let's say that our budget allows to hire 5 crowd forecasters. If we have that number 5, we can then use our model to estimate the expected error associated with the number 5, which gives that number 5 a quality stamp. For example, our model says that if we hire 5 crowd workers, we should expect a reduction of 80% in the variable error. Another way that we can use our model in practice is to first elicit the desired or the tolerable error from the decision maker, the person hiring the crowd forecasters. And from that one, we can feed our optimization model, which I showed before, and that optimization model will tell us the number of crowd workers to hire. For example, if the decision maker says, the requester says, that the requester desires a 0.96 optimal solution, our model suggests to hire 25 crowd workers. So to summarize our work, we proposed a novel mathematical model to select the optimal number of crowd forecasters. We have as an input a requester's or decision maker's desired or tolerable variable error. And our model can be used in practice in two different ways. It can also be used ex ante and ex post, before and after the elicitation of forecasts. Before, ex ante, we can use to estimate the ideal number of forecasters, and ex post, we can use to estimate the error curve. As future work, we want to do two things. Number one, extend our model beyond simple averages. That is how we aggregate the forecasts now. We want to try different aggregation techniques. And number two, we want to do forecasting beyond single point estimates. Right now, we're just eliciting numbers from crowd forecasters. Eventually, we want to extend that to different types of forecasting. And that's going to be it for my presentation today. Thank you so much for listening to me.